To exercise 4.1 on rate of change and differentiability. We talked about the idea of differentials or calculus. What's the point of calculus? Well, calculus is essentially the study of change, right? That's what calculus is. Probability, study of chance, algebra, study of patterns, etc., right? But when it's talking about calculus, it's a study of change. Before we can look at change, we have to look at where that is applicable, okay? In this case, we're going to be defining two things. First off is continuity, right? Whether a graph is continuous. The second thing is differentiability, whether at a specific point a graph is differentiable. We're going to first focus on continuity. A function f is said to be continuous at the point x equals to a, or at the point where x equals to a, provided the following all exist and are equal. So that is f of a. So the value you get for y when you substitute x equal to a, the limit as x approaches a from the positive side, and the limit as x approaches a from the negative side. Essentially, for a graph to be continuous at a specific point, all that needs to happen is that there needs to be a point, pretty straightforward, and it needs to be the same value from the left and from the right. Now, if a function is differentiable at a certain point, it must be continuous. We'll get to the second point later. But remember, if a graph is to be continuous, it must have a point, which must be equal to the point if you go to it from a positive side, and the same thing from the negative side. It makes sense, but that's just a mathematical notation. If you wanted to prove something was not continuous, you'd have to use this terminology. Let's look at the examples below. State the values for x, for which the functions shown have a discontinuity. In question A, it's pretty straightforward. It's pretty clear that the graph isn't continuous, right? I'm not sure if you can see that up the back, but there is an open circle, which of course means that it's not inclusive. The point 1, 2 is not on our graph, but instead 1, 3 is on the graph. Now I can just say x equals to 1. And technically speaking for this question, yeah, you'd get that right. But why? Why is the graph discontinuous or non-continuous at x equals to 1? I'd use my notation. I'm going to write that f of a, or f of 1 I should say, because in this case we're replacing x with 1, does not equal to the limit as x approaches a from the, and I'm just going to pick one of them from the positive side. If I go towards x equals to 1 from the positive side, it goes towards 2. That makes sense. But f of 1 is actually 3, right, according to my graph. Therefore, it is not continuous, or there is a discontinuity at x equals to 1. Okay. In this example here, on B, there are 2 points of discontinuity. Of course, the obvious one is this one right here, at x equals to 1. Without me writing it down, why is x equal to 1 a discontinuous point? At x equals to 1, f of 1 would equal to what? 2, right? That's what my graph tells me. At x equals to 1, f of 1 would equal to 2. However, if I approach it from the right-hand side, in other words, as from my limits, as x approaches 1 from the positive side, it's going to equal to 3. It's approaching 3. It should be 3, but it's not, so there's a discontinuity. It's the same example as before. This one's a bit different. At x equals to -1, you will note that as limits as x approaches -1 from the positive side, and I'm going to write f of x, does not equal to the limit as x approaches -1 from the negative side. There we go. As x approaches -1 from the negative side, it should go towards 2. However, in my graph, when my graph goes towards the -1 from the positive side, we should end up with negative infinity. Of course, negative infinity and 2 don't equal, so therefore the graph has a discontinuity at x equals 1 and x equals to -1. Any questions? I understand that this is something that's not typically touched on quite often, so please let me know if you have any questions. I'm going to move on. I'm going to leave question C for you to do yourself, but I'm going to move on to the next component. The next component here is that a function is differentiable at x equals a if f of x is continuous. So it makes sense, in order for our function to have a differentiable point, it must be continuous at that point. The other requirement is it must have a unique tangent at x equals to a. It must have a unique tangent at x equals to a. In methods in the current study design, we don't do absolute functions, so don't stress too much about the function shape. However, you might be presented with something, or you might see something that looks like this. So there's our Cartesian plane, and our function looks like this. It's literally two straight lines connected at 0, 0, but they go in opposite directions. At this point, from anywhere here and here onwards, it's differentiable. Right? There's a unique tangent at x equals to whatever it is. However, at this point right here, at 0, 0, how do we know if it's negative or if it's positive? There are quote-unquote two tangents that are available, aren't there? So if it's a sharp turn like that, it's not a turning point. It's just a sharp, it's changing gradient suddenly instead of gradually, then it's not differentiable at that point. Yeah? The same thing goes, of course, if our function actually has an open circle and the function itself is discontinuous. So if the function, let's just pretend the blue line's not there. If the function looks like that, the function doesn't exist at x equals 0, of course it can't be differentiable at x equals 0. So in this case, explain why each function is not differentiable at the given point. Now for this one, the first one, it says that f of x equals 25 minus x squared over 5 minus x at x equals 5. Well, I mean, x can't equal to 5. Of course it can't, right? The function is, f of x is discontinuous at x equals to 5, therefore not differentiable. Pretty straightforward. If it's not continuous, it can't be differentiable. And coincidentally, this function on the right hand side, our piecewise function on B, exactly the example I gave earlier. You will note that this one, instead of it being an absolute function, is just a hybrid function where we have negative x, positive x. Okay? Now, even though our function, negative x, exists at that point, right? Of course, two different functions, completely different gradients, right? It's not gradually changing like a turning point. Even if it's a very dilated turning point, it should still be, differentiable at the turning point. But because this is not a turning point, it's just a change of gradient. It's got two tangents, not a single unique one. Therefore, it's not differentiable. And then, of course, here, same idea as question A. X cannot equal to 1. Therefore, you get the idea. Okay. Any questions? All right.